Lesson 5-4, Archimedes Principle. Think of trying to push a beach ball underwater. It's really hard to do because the water pushes the beach ball back up. Turns out all fluids push things up because the pressure is higher at greater depths. This upward force is called buoyant force. If you remember, our pressure at lower depths was P2 equals P1, that's the pressure at the higher depth, plus rho GH. So since there's a higher pressure down below, then the gets forced up. So the buoyant force is the difference in the forces. Remember, pressure is force over area, so the force must be pressure times area. So it'll be the upwards force, the pressure times the area at the bottom, minus the downward force, the pressure times the area at the top. Factor out the areas. And then we had before, a couple lessons back, that the pressure 2 was pressure 1 plus rho GH. So if I subtract pressure 1, the difference in pressures is rho GH. So our buoyant force is rho GH times A. But density is mass over volume, so mass must be density times volume. And volume is the area of the base times the height. Therefore, the mass, if I substitute for the volume there, the mass must be the density times the height times the area of the base. Well, if we look over here for a force, that's the density, height, area of the base. So it looks like the buoyant force is the mass times g. Oh, but wait, mass times g is the weight. So this is the weight of the liquid that's displaced. That's Archimedes' principle. The buoyant force is the weight of the displaced fluid. So that's the amount of fluid that got pushed out of the way when this object was stuck in it. So our buoyant force is the weight of the fluid. If the buoyant force is greater than gravity, it floats. If the buoyant force is less than gravity, then it sinks. So that's gravity, or what do we call gravity? That would be the weight of the object that you've stuck in your fluid. So as you might have guessed, an object will float if its average density is less than the density of the fluid. In other words, it'll float if it displaces more fluid than its own weight. We can put this idea together with specific gravity. Specific gravity is the average density of the object. So this is average density of the object, and this is the density of the fluid. So that ratio equals the fraction of the object that is submerged. Since it's the fraction that's submerged, if it's less than 1, it's floating. If it's greater than 1, it sinks. So we have an ice cube, and it's floating in a glass of fresh water. The cube is 3 centimeters on each side. If the cube is floating, so a flat face is facing up, what is the distance between the top of the cube and the water? Well, the fraction submerged is the density of the object over the density of the fluid. Well, ice, if we look that up, the average density of ice is 917 kilograms per meter cubed. And if we're in fresh water, the density of fresh water is 1,000 kilograms per meter cubed. So that equals 0.917. So that means 0.917, or 91.7% of the cube is submerged. So to find out how much is submerged, I can multiply that by the 3 centimeters. Which is 2.751 centimeters, and that is submerged. So if I want the amount above would be 3 centimeters minus the 2.751, which is 0.249 centimeters above. A man once tied a bunch of helium balloons to a lawn chair and flew to a great altitude. And this really happened. He used weather balloons, but we're going to consider just the little latex balloons, like in the movie Up. If a single balloon is estimated as a sphere with a radius of 20 centimeters and is filled with helium, what is the net force on one balloon? Well, air, remember, is a fluid. So on our balloon, if we draw a free body diagram, we have our weight down and our buoyant force up. Now the weight would be the weight of the balloon and whatever's inside of it. Whatever's inside of it is helium. So if I go F equals ma, if I add up the forces, that's the buoyant force up minus the weight of the helium down, and that equals my net force. I don't care about the A yet. Just looking for the net force. All right, so to figure out everything, the volume of a balloon, it's a sphere, so its volume is 4/3 pi r cubed. Should be 4/3 pi times 0.2 meters cubed, which is about 0.03351 meters cubed. The buoyant force, well, what are we in? We're in air. So the buoyant force is the mass, it's the weight of the air. So it's the mass of the air. But remember, density is mass per volume. So mass must be density times volume. So that would be the density of air times the volume times g. Well, density of air is 1.29 kilograms per meter cubed. Our volume that gets displaced would be the volume of the balloon, because the balloon is pushing air out of the way, and g is 9.8. So our buoyant force is 0.4236 newtons. The weight of the helium, well, same idea, it'd be the density of the helium times its volume, that'll be the mass, times g. So density of helium is 0.179. The volume, 0.03351, and g is 9.8. So the weight of the helium is approximately 0.05878 newtons. So our net force, there we go, is our buoyant force minus our weight of the helium. So our buoyant force was 0.4236 minus the weight of the helium. And we get 0.3648 newtons for one balloon. All right, I'm going to erase this. How many balloons would be required to lift a man and a chair? Well, now we've got, so we sit in the chair. So we have all these balloons, so it's the buoyant force times all the balloons. So we'd have to multiply it by x, x being the number of balloons. And we have his weight downwards. And our weight of the helium times x. So our net force, if I go F equals ma, our forces upwards are the buoyant force times the number of balloons. Downwards is the weight of the helium times the number of balloons, and the weight of the man in his chair. And let's say no acceleration, let's just barely go up. So this is what we already figured out up above. So that would be 0.3648 newtons times the number of balloons. The weight of the man would be 80 kilograms times 9.8. Move the weight to the other side, which happens to be 784 newtons. And divide, and we get approximately 2150 balloons. That's a lot of balloons. Be buoyed up by the thought of the joy derived from solving these problems. Have a good day.